Yes, hello, good morning. And am I audible properly?
Yes, ma'am.
Yeah,
Yes. Okay, so I'm just sharing my screen and recording also. So today we are going to start with a very important, that is, it makes your whole of analog. Okay, and I hope I'm audible. Yes, anyways, yeah. And one thing, this in your textbook that I have shared with you, this is chapter 5 here. Okay, and I had talked to you a little bit about BGT last time. Now, as the name says, this is a transistor basically, and transistor means it can be made to work as an amplifier in analog circuits to make filters, amplifiers, and of course digital. Okay, but in today's date, the digital circuits that makes mostly 80% almost of your total application, right? It is in IC form, integrated circuit. And what goes in an integrated circuit, if I want to make it more clear, right? You know how the IC looks. Uh, IC, let's say. So bear with this little background noise because this vegetable walas, they all come and go. So what is this? First, I give integrated circuit. Okay, so you know this how this circuits this integrated you have all seen, but what this is made up of all inside it is made up of transistors only. But which transistor? It is known as MOSFET. Okay, and BJT also we will show you in the lab. So BJT, and we I think what is opening bipolar junction transistor. See, this is how it looks, right? And like you can have it, you can, it is in mm, few mm by few mm. So this is the transistor, and in an integrated circuit, what goes is a MOSFET, which looks like this. Now the dimension, because very important is you should understand what you are doing and why you are doing. Right, so this is how a MOSFET looks. Okay, so inside this integrated circuit, it is an ocean of sea of such MOSFET. These are also transistors, like it is a small brother of BJT, and the scale of this is in micrometer. Okay, so 10 raised to minus 6 of the meter you cannot see with your eye. It is that small. And the digital circuits are made in this, they are in this IC, which is made up of this. We are studying is this bipolar. We can definitely make a digital circuit, but now you can understand how big your digital will be. Okay, and since this is big in size, it can have, it can tolerate, or it is used in circuits where you need more current and more voltages, that is in especially in your power supply or applications like accelerators and other applications where you need in all analog you can say as an amplifier. So if I am speaking and there is a microphone, and now in so it goes to the amplifier first stage, right? As I have been talking to you, to remove the noise, it goes to the filters, all these analog circuits, and they are made up of just few transistors. But it is a challenge. Okay, design is a challenge, and that's what is about BJT. And we will see both analog digital part of that, but it mainly, as I said, it used applications where the initial stage when the signal is generated, okay, it is has to be amplified, filtered, converted into digital. So and then power units, as you know, they are high voltage high power devices you need. So this is where in today's date also it is used. Okay, and this is, if you understand easy to understand MOSFET. You can on your own almost. So, is that clear? Am I audible? No, the connection is lost.
Voice is cracking.
My voice is okay. So let me again come back and go and come back. Sorry, am I audible now? Hello?
Yes, ma'am.
Okay, now not cracking, right?
Yes.
It's not cracking, right?
I'm cracking a little
It
bit.
still is.
Okay, still cracking. I don't know. I mean, my connection is all fine only. Let me once again check. Still cracking? Let me close all this. So in short, this is your chapter 5. Is it cracking? One of you unmute unless and until it is... hello?
No,
it is
no,
still
no.
cracking?
No.
Okay, thank God. Okay. So, yeah, so this is basically, as I said, I gave you where in today's date it stands. It is still used, okay? And as the technology has advanced, we are able to have in the MOSFET also now high voltage, high current MOSFET, okay, which can do same job like this BJT, but it is very expensive. So that fabrication and technology is very expensive. So I mean, if we are not targeting an application, right, where you can spend much money, then these BJTs are only used, and it is, I mean, already it is used only in exceptional cases, like let's say in astronomy or satellite applications, where the weight matters. In that case, only such ICs using MOSFET will be used. Okay, high voltage, high power. Otherwise, it's all BJT there in your power. There is a power unit in all the applications that has these transistors. So here, so it was invented in 48 at Bell Laboratories. Okay, so they were the pioneer, and it was a new era of the solid state circuits, we say. So these are see, before it was vacuum tubes, and your electronics was with mechanical parts. Okay, your first computer was whole mechanical in form. So it was really, really big, these mechanical parts. And that's what. And it was replaced by MOSFET as predominant transistor used in modern electronics. So initially, your electronics was with big, big boards where we used this discrete component. And this BJT, it is made up of three mainly parts. It is made up of three these units, subunits. That is, we can say emitter-based collector, and which is nothing but they are back-to-back connected diode. So here also we have two flavors. One is NPN, as you can see, and the other is PNP, which is a complementary form of the same transistor. Now, when we make a circuit, okay, the performance parameters are area, delay, power. And area, now with miniaturization or area to jo lagta hai, what it takes space it will take. But then two things very important is power requirement and the delay, because it should, the response time when you switch on the circuit, the bulb should glow. It should not glow after few minutes, right? The response time should be very fast, and these are like, hundreds and thousands. In today's date, it is millions and trillions of transistors, and if all of them takes time, right, then the cumulative delay you can understand. So the delay has to be very, very low, and at the same time the power, there cannot be any leakage. So now if I have to explain in terms of power in a layman way, right, let's say if I'm drawing just an inverter, as a black box, right? So you know that to an inverter, if you give an input, so I'm giving an input, I'm getting an output, and let's say a square wave is my input. If I give high, I should get low, and if I give low, I should get high. Okay, so now what happens is, in this inverter also, it is made up of basically two transistors. Okay, so if it is a BJT, yes, both are BJT. If it is a MOSFET, both are MOSFET. For now, forget MOSFET, our goal is to study BJT, but whatever you can do with the BJT, yes, same way you can do with the MOSFET. So if the inverter is made up of two BJTs, right, the upper one is PNP flavor, okay, PNP, and the below one is NPN, okay. So here what happens, we will see that both are complementary, that when one is on, the other is off, and vice versa. And what you give here is your battery. Here is, of course, the ground. We should not forget ground. So and then this is the load. It can be another stage of an inverter. Just try to understand in a layman way. It will be another stage of an inverter, NAND gate, NOR gate, or whatever. So this is let's say a black box. So to the equivalent of this, we can, as the input capacitors, okay, that we can give here as a capacitive load, because it has some input capacitance. If you cancel this, it can be replaced by a load with a capacitor, or R and C, right? So, but C affects more, so capacitor is, and then what happens, that when you are giving 1, right, the output should be 0, and then when you are giving 0, the output should be 1. So what happens is, when you are giving, let's say I will start with 0 first. When you are giving 0, right, at what happens when it is 0, this transistor is off and this is on. When this is on, this is shorted here to this point, and the capacitor will charge. So when this is 0, the capacitor will charge to maximum, and when it is 1, the capacitor will discharge to, when it is 1, at that time this transistor is on and this is off. Okay, and what happens at that time, this capacitor is grounded, it is short to ground, and there is a path. Okay, and it will discharge to 0. So when it is 1, it is 0 at the output, and vice versa. Here what is happening is, the goal is, see, discharging, depending on the input, your circuit, right? This energy is given by this source. Okay, so this is where your energy from your supply, the energy has to be transferred to the load. Okay, this is the place where your energy has to be transferred. Your energy cannot go to the ground. So if there is a path from here to ground, then it is wasting your energy. Okay, if the current is flowing directly from the supply to the ground, then your current is wasted, your power is wasted, and the power, there is unnecessary power dissipation. You can say there is a leakage. So we will avoid this condition. And in order to avoid this condition, both of them cannot be simultaneously on. At a time, only one will be on. Okay, so what happens is that when we have this signal, only when it is doing a transition from low to high or high to low, right, at that time only, for a fraction of a second, both will be on, and that is the time that some energy or some current will be lost to the ground, and this is the leakage. So to minimize the leakage, we use this complementary. Okay, we use NPN and PNP. So if it is one input, if you have a NAND gate, right, which is a 2, NAND gate means 2 input, then you can have 3, 4. So depending on the number of inputs into 2, you will need that number of transistors, but this gives the best power. Okay, the least power it consumes, and all of them must go to the load. That's what it ensures. And the very important thing in digital is noise margin. Okay, So in noise margin, so when you are making analog circuit, you can do the same circuit using N also, and you can do the same circuit using P also. In analog, we don't use at a time both N and P. In some cases, yes, later on we may see some applications, but usually it's just one or two. One transistor makes a single amplifier. Then if you have an amplifier followed by another stage of amplifier, there also, right, the single transistor is needed in your design. If it is multiple stages, then yes, multiple, and it can be, your amplifier can be with P and either of them. But I'm talking of the digital circuit, but nowadays it is mostly on MOSFET, and the same principle applies to MOSFET also. The very important criteria in, again, in digital is why we use complementary is noise margin. Now you must have heard of noise margin in your digital DLD or somewhere, I don't know. But what is noise margin is that when your signal is propagating through your circuits, okay, this is one circuit, then this is another circuit, third circuit, it is propagating, right? Then and then it is getting the power from the supply. Remember, every circuit gets a power from the supply, so the output of this goes as an input here, and same way, and then the output. So let's say these are all digital blocks. So when the signal is propagating, it should not die out. So let's say that this the swing that this circuit can take is 0 to 1 volt, okay, and it is getting instead of 0 it is getting 0.2 volt, yeah, instead of 1 volt it is getting 0.8 volt as an input. Okay, so if it is 0.2 volt minimum, 0 is, instead of 0 it is getting, due to some noise added or attenuation in the signal, it is getting 0.2. Then 0.2 should, even if it is not a 0, right, that 0.2 should result in 1 here, and it should not result in 0.8 or 0.9. If that happens, if every stage the signal gets attenuated, it will finally die out, or 0 will be treated as 1, yeah, 1 will be treated as 0. So we don't want that, we want the signal to be recovered. So even if it is 0.2, yeah, 0.3, the output here should appear as 1. Okay, so if I show you this graph, if you have seen before or not, I don't know, but here in this course you will see. So this is the graph of an inverter, the characteristics. This is the input, okay, and this is the output. Okay, so for an input, okay, if you have, so if this is 1 volt, I will take 2 volt, okay, 2 volt, and let's say this is 1.2 volt here. Okay, this point is 1.2 volt. 1.2 volt, and for example, okay, and then this is 0.8 volt, let's say, right, 0.8 volt. So what happens is, and similarly this is 2 volt, your output side. So let's say from 0.1 volt to 2 volt, right, even if your input is, right, your output is going to be still 0, and even if your input is from 0 to 0.8 volt, right, this is your input 0 to 0.8 volt, your output is going to be still 2 volt. Okay, so my point here is that the signal, the circuit should have the capability to recover. If this characteristic curve would have been like this, instead of what I drawn like this, it would have been like this. Then if your output is instead of here it is 1 point, here it is 2 volt, let's say, then here it is let's say 1.5 volt, right, then your output will be what? It will be around 0.5 volt, not 0. In this case, it was recovering, right, your signal, if this is the graph, and this kind of graph you get with complementary setup. So noise margin is another factor in digital, which is very important, and for that you need both the flavors. Okay, so just try to understand that in detail when we go through this BJT, we will see all these things. But so that you are not wondering, I tried to make a point in an easy way. Okay, so now forget everything. Let us come back to our device, this little device which has back-to-back connected PN junction diode. Okay, so what you have is that this kind of setup NPN, and we have like 3 terminals, and these 3 different sections of this as per NPN. The first is emitter, then we say base and collector. This is the terminology that is given, and you have 3 terminals at all these 3 places. With this is a metal contact, and the terminals that connects to the external world. Okay, and these are emitter base collector, and since you have three terminals, you can connect two voltage sources, and only if you connect two voltage sources, what you get is a current. Now to get a current, you need to generate the carriers first. Okay, and then that carriers will make a current. Okay, so if you want a river to flow, first you will need water, then the river will flow, right? So either it will flow because of some force, or river always flows from up to down, right? So here also for the current to flow, here we don't have that slope that it will flow, right? So it is not that way like the river. But here how it flows is that you give energy, right? So that energy should, so if there is the electrons have come and settled, first you have to generate these electrons. It will come and settle, and then once it is settled, through an external force, that is a connection, a battery, we will drag this. Okay, it is like a vacuum cleaner. So that is how we will see how. So now there are four ways that you can connect it to your battery. So this is one terminal, this is one junction. Okay, so as from PN junction diode, you know that this is one junction, this is the second junction, and you will make connections across emitter base and the second battery from base to collector. Okay, so two batteries, emitter to base, and then another one will be from base to collector. And what you can have is that here, or it can be in forward or reverse, or here also it can be in forward or reverse, and there are four possibilities that you can make a connection. Now, based on how you connect, this device is going to operate. Okay, so now there are a few things. Now you understand there is one domain analog, another digital. So if you connect in some way, it will work as an analog circuit. It means you can use it as an amplifier. So you have to give that way the voltage so that it will work as an amplifier. If you do not, then it will not work as an amplifier, and it will work in some other mode. So let us see that mode. So now see, these are the modes, that is cutoff, active, reverse active, and saturation. So you have two junctions. Now that picture in mind, you have EB and CB. And if both are reverse biased, okay, so if both of them are, if this is reverse biased and this is also reverse biased, then the region is cut off. Okay, means it is dead. It is no current is flowing at all, of course, right? Both are reverse biased. So, and then in diode, you know that, so this is diode, these are two diodes, right? So if you want emitter, as the name says, will emit the electrons, because you have to, if you want the current to flow, you need electrons to be generated, and that's the job of the emitter. Okay, the base here facilitates the flow of the current, we will see, and the collector will collect, and it will collect the electrons, because collect means here what basically, it will make it run, which means the electrons were there but they were not making a current, but this collector will help to make it run and hence create a current. So that is the job of the collector, and the electrons will, whatever was generated here will come here. We will soon see that. So whatever I'm speaking is making sense to you all, or am I going fast or what?
Ma'am, I am having a doubt. Madam, here earlier you made a point that the power should not go to the ground. Can you please repeat that point?
Okay, see, my point is, see, this right now what I'm explaining you is NPN. Okay, there is also another flavor. I mean, if you have PNP, right, the way it is doped, this is positive, negative. So you will have these two flavors, these two kind of BJT. There are two types of BJT, NPN and PNP. What I was explaining you is that where you will need PNP. Okay, so when you are making analog circuits, that is as an amplifier, which you will extensively study in this course, because amplifiers are everywhere, right? In your embedded applications, to every applications, your phone, your TV, everywhere there are amplifiers. So extensively you will study here is an amplifier. In amplifier, you can build amplifier using either of them, either NPN or PNP. लेकिन दोनों कहाँ जाएंगे साथ में? So both of them will go together in digital circuit. So digital, the simplest digital circuit what I was talking to you is an inverter. Okay, it's the simplest digital circuit is an inverter. Now this inverter is made up of, you can make an inverter using either, okay, using either NPN or PNP, just one transistor. But in that, for any circuit, the performance parameters are area, delay, power, and in digital it is noise margin also. So 4 parameters. Area is okay, whatever it needs, and we will give that area. Okay, कि जो भी area चाहिए to build that board. But the main things are power, delay, and noise margin. Power means if it is nowadays everything is mobile, if it is given through a battery or even through your supply, it should not consume too much of power unnecessary. So as an engineer, our job is to make the best circuit which consumes least power. So that it consumes least power, it is necessary to make a circuit that is complementary. So you will have, if you are making an inverter, it will have 2 transistors, okay, that is PNP, the upper one, and NPN, okay, and and then you are giving a signal when it is low, right, you will get high, and when it is high at the output, you should get low. So that is what I was explaining. See, we need not waste too much time, just try to understand that this circuit, how it is connected, that I will show you later on, not to confuse you. That this is for an inverter digital circuit where you have PNP, that is this one connected, and then you will have NPN, okay, so that is here down, and to the PNP this VDD will be connected, and here it will be grounded, okay, and then there is you think this as a black box, and there is a capacitive load which is equal to the input capacitors of the next circuit, okay. Here you are giving an input. So my point to you is that if it is high, right, here it should be low, and then when it is low, it should be high. So now what is happening is that when it is high, the input is high, okay, at that time, let me start with low so that charging, discharging, it is easy for you to understand. When the input is steady low, at that time, this is on, your PNP is on. We will see that all because I have just started. But I'm explaining you where it is used and why. So that P will be on, N will be off when the input is 0. This NP and this transistor will be off when the input is 0, but this guy will be on. They are complementary. So when this is on, this point VDD is connected to the capacitor. Okay, so this is now like a short, and it will charge the capacitor. So your output will be, when the input is 0, output will be 1. Okay. So when this is 0, the output will be 1. It is 1. Okay, and then when it is 1, the output will go to 0. It will go to 0. So then when it is 1, right, at that time what will happen? This will be off, and this guy N will be on, and there is a ground here. Okay, so this will be on, so this capacitor will be shorted to the ground, and it will discharge. And hence the output will be 0 because the voltage here it has discharged, it is 0. So the point here is that this is the load. Whatever energy is from VDD is giving the energy. That energy should go to the load, because it is the load, it is the next circuit, next stage of this circuit that should get this energy in terms of voltage that is developed. Okay, it should not go in vain. That what I mean is, it should not go as a leakage, that it will be leaking and going to the ground. It should not take the other way. It should only go to the load. Now, other way, when it will go to the ground, when both are on simultaneously. So both are on simultaneously only for a fraction of a second, when it is moving from low to high or high to low. At that time only both are on, and then it will get a path to ground. And this is a leakage, but this is the least thing. This is for a fraction of second, and that is fine. We cannot make better than this, because the transition will make it, for a fraction of a second, both of them on. But after, otherwise, there is no leakage. Okay, the leakage is only when it is getting a path from VDD to ground. And that, because when one is on, when it is steady, the input is either low or high. When it is steady, either of them is on, not both are on. And when either of them is on, there is no path from VDD to ground, because one is off, right? If you have a VDD to ground, VDD and this is ground, and there are two segments here connected. If one is open always, right, then there is, if either of them is open, then you don't get a direct path. Only when both are on, then there is a path. And the leakage is only when there is a path from VDD to ground. that much. Your battery is losing that much. It is not going to the load, but it is losing that much of energy or current, and it is going to the ground. But that is the best thing we can do. It is only for a fraction of second. When your input is steady, either 0 or either 1, at that time there is no power dissipation. That was
Yes,
I was
ma'am. I got it. I got it. Ma'am. Thank you.
but you will understand in detail. But you should not be wondering if I just tell you in short why P and P in digital circuit it is used, then you will be wondering. So I don't want you to wonder. That's why I said you. But we will see in detail when we in near future. Okay.
Okay, okay.
So now let us bring our understanding to NPN, and it's working. We have just begun. So so with this NPN now, so see, this is an electronic device, and when you give a voltage, a current is developed. It is very important to understand, as I said now, that these are three regions, three terminals, two voltage sources. How you connect, as you can understand now, is very important, and it will decide whether it can be used as an amplifier or in which mode. So if both are reverse biased, then no current will flow. No, both are reverse biased, no current is flowing, and it is in cutoff, right? It is dead. It is like not there. It is all open. So it is we say cutoff mode. Okay. When EB, emitter base junction, is forward biased and this guy is reverse biased. If you give voltage such that this is forward bias, this is positive is connected to positive, negative is connected to negative, and this is connected such that this is connected to negative, and this is with respect to this is positive, right? Then we will see that all, don't worry. So in short, this is forward biased and this is reverse biased. Okay, then this is the mode, active mode. We will see all in detail, don't worry. And then the other way, that this is reverse biased, but this is forward biased. Okay, then we say it is reverse active. It is active but reverse active, and we will see in detail. And then if both are forward, we'll say it is in saturation. If you want to make it use in the digital circuits, we use this on and off. You say switch is off, switch is on, off, on, off, on, off. If you want to make an amplifier, this compulsorily has to be forward biased and this compulsorily has to be reverse biased. And then only you can use as an amplifier, and this is biasing basically. You have to give proper voltage, like in diode, we gave enough if it was your input in diode. If you want to rectify an input which is in millivolt, and if you give directly to the diode is off in millivolt. Only after 0.6, 0.5 volt it will be on. So what you do, you give a DC bias, right? So that is 0.6, 0.7 volt. Ensure that it is in the operating mode, and to that you superimpose your small signal, right? So that are the conditions. If it is a little signal, then what? You cannot operate. So these are the ways, right? So here also this transistor amplifier means the input to the amplifier is again in millivolt. The current is in milliamp, and then we want to amplify that. Okay, so these are the devices that amplifies this range of current. So yeah, and then if you connect the other way, it is reverse active. Although I will soon explain you that in this mode hardly what we don't use this mode, and why, that I'll explain you. See, another thing that you must understand is that this is the diagram to show you in a simple way. Okay, a simple schematic of this. In reality, the device is structured this way. Okay, so this is emitter. It is surrounded by this base, and this is the collector. Okay, so the collector is big. I'll come to this point, but this is how it is fabricated. So this is the list. It has this area here, and this is bigger. What is emitted? Emitter emits, right? And then base, and this is collected here, and it comes out through here, collector, correct. So in reality, it's like this way for simplicity to understand in the first stage, right? Slowly we will go ahead. So this is your how the device is, and it has two junctions and two voltage sources, but the current is only one, and that current is what you get is like the diode current, this is the collector current. Okay, but internally there is emitter through the base also, we will see all those things. So two voltage sources, now you understand very well how it is connected. And this, there is another flavor also, mostly used in digital, although also in analog circuits. Whatever you can do with this NPN, same thing you can do with PNP, but they are complementary in nature. Okay, so once you have little understanding of NPN, I will throw more light on PNP, but otherwise they are complementary. So let us go ahead and we will understand first NPN properly, and that will ease your understanding of PNP also. Now, let us understand, we are here for analog. Digital also, once you are done with a little of analog, we will see digital, which is not, once you understand. See, analog is a base of digital. It's a mother of digital. So understanding analog is very important. If you understand once this, digital is not a big deal. Okay. So analog means this is the basic physics in short. It's analog is not a different unit of area of understanding. So this is the physics basic and electronics. So here we will first understand the active mode I talked to you, because that is very important. Okay. And then other modes, we will see all of them, but they are comparatively easy. So if you understand this first. So an active mode is the one which is used to build your amplifier. Okay, so that point of view, you must, when you are thinking, it is an active mode for now. And if you see here now, you are comfortable with this NPN and these two junctions here because of the two semiconductor slabs connected back to back. Now, if you see here also, now as talked here, right, this is forward biased emitter base and collector base is reverse biased. So now let me explain you. So this, when you give this voltage, this is N, this is N, this total line is N, and this P, right? So this is connected, and this is what? Forward biased or reverse biased? If I connect this way, this EB is forward biased or reverse biased?
Forward bias.
Forward.
Forward biased. Very good.
Forward bias.
And now, very good, very good. And if you see, this is again N, this is connected to P. So this is reverse biased, right? And this is, if you connect this negative here like this way, this is reverse biased. Agreed?
Yes, ma'am.
Okay, so this is forward bias, this is reverse bias. Now, in a simple way, if I have to explain you, just be attentive, although every detail we are going to see. Now, if this is forward biased, it will work like a forward bias diode? This EB
Yes.
emitter.
Yes, ma'am.
And what you will have as a result of that, now understand, this is N. So that is that this is rich with electrons. This is rich with holes. When you give a voltage, it will get an energy and it will try to diffuse. Diffuse means from higher concentration to lower concentration. And the electrons will come from here. They have only one way and they will enter the base. At the same time, this base, which are less in number, okay, base is very thin. Base is very thin. And this is lightly doped compared to this. Although both are doped, but this is heavily doped. So if there are 100 electrons, hardly there will be 2 holes, let's say. So those holes will come here and these electrons will diffuse here, right? As you very well know, diffusion because of the difference in the concentration, and it will diffuse. And since and then they will recombine, but since the sun will come here, they will recombine with the hole. But since electrons are more, like 100:2, let's say, then the current will be because of the electrons. So the minority carrier here in the p-type are electrons, okay? And the majority are hole. But since electrons are more in number, they will overtake, so if it is recombining, still you will have 98 electrons, okay? And that will make your current. And now what happens when you give a voltage, then this guy, electrons move here, these holes move here, some will recombine. So holes are utilized. So new holes, from where will it get? Through this potential here. Okay, so new holes will be generated but compared to this, it is 100:2 kind of a ratio. You can think that way. Okay, it is very less in number, and one will move here, then one will recombine, but the current is then because excess of electrons, the current will be because of the electron. But now what has happened is that this potential was to this only, and the electrons have come and they are all settling here. Okay, but still it has not made a current. The current is only, this is a device and it should give out a current. Okay, so how to get a current, how to make them run or move? It is only, now electrons are what? Negative. If you give a positive voltage here, okay, if you give a positive voltage here, it will attract these negative electrons. So this is like a vacuum cleaner. It will suck all the electrons given the positive voltage here. To give, if you, how to give a positive voltage here? By reverse biasing this junction. So if you reverse bias, meaning if you give a positive voltage, then whatever the electrons are collected here and that you have agreed will be sucked, and it will zoom, it will move inside this. So the electrons will come here, and that is IC. So now you have, what you see here is IE, the current because in the emitter. Then IB has two components, the one which has injected here and the one that has recombined with. So if there are, like, let's say two, let me take 4, okay, or 5 holes, okay, then 2 will go here and 3 may recombine, or 3 will go here, 2 may recombine, and if there are 100 electrons, still 95 will be there. Okay, so the current is because of the electrons, which will be, that needs to be moved here at this terminal. How to do? If you give, because they are electrons negative, if you give a positive voltage, it will suck all the electrons and it will come out of here. And that's how a current is created. Okay, so here if you see, this is the direction. So here if you see what comes, so now see, this is the total thing, IE. So IB, so electrons are moving this way, of course, without no doubt. In NPN, this is NPN, and this is active mode because we are connecting this in a forward and this is in the reverse biased region. And this is how the electron moves. Okay, and this is the flow of the current. The current is moving this way. Here, this is, the arrow is outside, and here it is this. So your current is what? IB. Okay, IB plus IC is IE. So if 100 electrons are getting generated here, let's say, okay, then 98 will make here. 98 of them will make here, for example. Okay, so something like that. And then 2 will be here, let's say. So it's like, you know, this plus this is making this, because this is the pool where it is generated, some in recombination, and the others will make it as an IC. So see, this was a very simple understanding which you may never forget. So that's why reverse bias is, as long as this is reverse bias, now you know that in diode, that reverse bias, right, this is all reverse biased. And then in a normal diode, it will break. Okay. So as long as it is this voltage or this voltage or this voltage or this voltage, it is reverse biased. So whatever, this should be reverse biased, either at this voltage, this voltage, this voltage. It should not break down, of course, but in the reverse bias, whatever the voltage it should be, it is okay, but it should be reverse biased. Then, so now what you understand is that this is the current, okay, IC, and it depends on what? It doesn't depend on this VCB. As long as it is reverse biased, it can be if this is breakdown at 5 volt, if it is 1 volt, 2 volt, 3 volt, 4 volt, whatever it is, irrespective of that, it should be reverse biased. Only is the condition, right? The current will come out, the electrons will come out. So the point here is that IC will not depend on VCB, but IC will depend on which voltage then? Who will tell me? Hello? Am I audible?
Yes, ma'am.
Yeah. So you understand now, IC will not depend, as long as this is reverse bias, this IC is not depending on VCB, but it depends on what? Which voltage?
VBE.
VB બીજું છે શું અહીંયા referring બે તો છે, right? So it's just two voltages you have and it will depend on VBE because IC is proportional to IE and IE depends on VBE. समझ में आयो?
Yes, ma'am.
And in your circuit, when you are using, this VBE will be as an input and it will generate IC which will go to the load. So your output, this will be when we are using in the circuit, you will soon realize the things. This will be your output current which will go to the load and this will be your input voltage. So your output current will be proportional to the input voltage. Okay, that's how. So just think that way, but that is later on because this is a device where you will give some input, you will give some energy and that will make the current and then things to run and work, right? So in short, this was to generate the flow, the bulk of electrons, you can say, and this was to give it a motion. And your IC is not dependent on VCB as long as it is reverse biased, but it is dependent on VBE. Right? And in analog, this is important mode because if you don't bias this way, you cannot make it work as an amplifier. Okay, any queries with this? You can ask me. Otherwise, I'll go to the next slide.
Hello, ma'am.
So, bolo.
Ma'am, why it is not depending on VCB? Like the VCB, the voltage will suck all the electrons from that reverse bias.
Yes. See, okay. Let me tell you once again. Without any hesitation, you should ask. See, reverse biased means this is junction, na PN. So this is reverse bias curve. You agree with this?
Yes, ma'am.
If this is forward, so you can think this part. Now we are talking of this and this junction, which is known as CB, collector base junction. This junction we are talking of. See, અહીંયા તો electrons આવીને ભેગા થઈ ગયા. They have settled out here in the base. But it has to get energy now. See, it cannot come out of the base because here we are giving this as an input terminal here. Okay, it has 3 terminals, and if you want the electrons to come out from here through collector, અહીંયાથી electrons ને બહાર કાઢવા હોય, right? Then we will not go and catch it now till you come out. We will not give our hand that you come out, right? How will it come out? Now electrons have come and settled and they are waiting to come out. So to come out from here as a collector current, to make a current through this terminal collector. This is a terminal, there is a metal and then there is a wire which you can connect and then the current should come out of here. How will it come out? If you give a voltage, you have to give a voltage. See, these are negative. And negative, unlike charges attract and like charges repel. You agree or no?
Yes, ma'am.
So if you want to pull this, it's like a magnet, right? So if this is negative electrons and if I want to attract it, I have to give a positive voltage. So this positive voltage will attract the electrons. So this potential or this electric field here will work like a vacuum cleaner. It will suck all the electrons here. You cannot keep it inside, no, these electrons. It has to make a current. It has to come out.
Yes, ma'am. But what I am saying that if VCB, we increase the VCB, so that positive voltage increased. So the more electrons will come out.
So I got your point. Now, this is fine with you, but you are only telling that why doesn't this matter? Yeah. Okay. So now
yes,
let you, if I ask you that for this junction CB, if I give, let's say this is breakdown is 5 volt. 5 volt is breakdown. If I give 1 volt, it is reverse biased or no?
Yes, ma'am. Reverse biased.
If I give 2 volt also, it is reverse biased or no?
Yes, ma'am. Up to 5 volt, it will be reverse bias.
So that's what, that as long as this is reverse biased, if what I meant is that if you give 1 volt, if you give 2 volt, 3 volt, 4 volt, it is okay. The current IC you are getting is not dependent on this. This is the job it is doing, is to suck the electron. As long as this is reverse bias, the number of the current here, IC, the number of electrons, it depends on VBE. Because IC is made up of IE and IE depends on VBE. Although you are right that, okay, that we will see later on, it will make little difference, but that is very, very little. Okay, we will see that. So the current
Okay,
that it gives at 1 volt, if it is 100, then at 2 volt, it will be 101 electrons, let's say. But that is not much. The base of your work or understanding is that this, and that physics also I'll explain you, but we'll come later on. But this is simple and short and crisp, that this IC doesn't depend on VCB as long as it is reverse biased. It depends on VBE. Itu kena samjhanu ne?
yes, ma'am. That's understood.
Yeah. But you are right. If it is 1 volt or if it is 4 volt, if at 1 volt there are 100 electrons coming out, then at 4 volt it will be 102, 103 electrons coming out. But that we will see. All right. If there are 100 electrons coming out at this volt, at 4 volt, then 104 will come out at 100 volt, for example. That we will see later on. But that is very minor. Okay.
Okay, thank you.
Okay, so I hope that is fine. This is the flow that electrons, this is the flow of the current. Okay, electrons will move like this way and come out. So I see this is the current flow is opposite to the flow of the electrons. So IC is this way. And then as you can understand, IC plus IB is equal to IE. As I said, if 100 electrons are generated, 2 will be lost here in recombination, 98 will make it here in form of a current then. Will cause current to flow. This current has 2 components, electrons injected from emitter to base, you have understood, and holes injected from base to emitter. Okay, so, and it will be shown that the first of the 2 is desirable. So this is the one that makes your current at the collector. Okay, and this is achieved with heavy doping of emitter and light doping. So this is heavily doped, this is lightly doped. And emitter current, so this all understand very well. This is the base of your work, and this is the current IE. So see, in short, you have 3 currents, IE, IB, IC, 2 voltages, and you have to understand that if in terms of quantity, if it is forward bias, reverse bias, then what will happen to this current? And this current, as I explained you, this will go to the output, it will go to the load. Means that if you are making, let's say, a black box, if I'm showing you, and you are making an amplifier A, okay, and that amplifier has this one transistor, we will see the whole circuit, think it as a black box. All the circuits have a supply, VDD, this is the energy. Okay, VDD, this is the energy. Then there is a ground, if you take this as an amplifier, and then there is an input and there is an output. So this is an amplifier, and then your input is plus minus 20 millivolt, and it is amplifying, let's say, 50 times, right? Then what will be your output? So you multiply, so that will be your output. So it is an amplifier where this transistor will, one transistor is going to amplify. So what it will give, so it will develop a voltage as we talked, right? So that voltage is because of this current, IC. So IC is at the output side, and this VBE will be at the input. Whatever you are giving at an input will be at this. This will be making your input, and your output, which is in proportion to your input, right, will be making at the output side. So this is at the output. This is at the input. So your output depends on, this is the current that is generated. It depends on VBE, in short. Okay, we will see this is what is your course about. So emitter current IE is the current flows from EBJ, flows out of the emitter lead. Okay, as you have seen here. This is flowing out because this is moving this way. And minority carriers in the p-type, these electrons will be injected from emitter, right? All these electrons will come to the base and in the opposite direction. So minority carriers in the p-type region, because base is thin, concentration of excess minority carrier within it will exhibit a constant gradient. Now understand this. Now slowly we are coming towards we want to get an equation. See, one thing you must understand, that mathematics speaks of the whole universe. Okay, a picture speaks of 1,000 words. Mathematics speaks of the whole universe. Forget this device. So unless and until, if you understand everything, you do it practically also. But if you cannot put down in a form of equation, that theory is not accepted. And whenever you are making circuits, it is couple of components, circuit analysis, many transistors going, you have to do analysis and design. Okay, so the engineer main job is, once you are good with that connections and all, anybody can do. But main is design and analysis, that you know that, okay, my sensor is giving me output in this range, or I want to rectify this, so I will need this will be my output, all those things. So specification, from the specification you design. To design, you have to analyze, and for that you need set of equations. So all this physics will help us to derive equation. And once your equation gives a result, okay, the equation will give you the same result that you see when you work in the lab, or almost, okay, 5-10% here and there is okay. And or if you are doing simulation, because when you are simulating, what is there at the back? When you are simulating your diode, at the back is the diode equation that is running. Okay, there is no magic happening. So, and that is what our devices are good. Your computer can easily do that. Okay, it doesn't have to think. If it has to say hello to you, it has to think so much. You will have to do all artificial intelligence and this and that. But to do an equation, it doesn't have to think. Okay. So the point here is that because any electronics you develop, it is a complex design, in the sense there are a lot of devices, components, and there will be R, C, they all have different equations. And then you have to do circuit analysis. So equations are otherwise also necessary. And unless and until it is not proven by an equation, it is not accepted. And these are already more than half a century old physics and analytical equations that have been developed, and it holds, right, because it's the same device. So now slowly we have to develop the equations, and the main goal is, when you study, that's why I have been asking you that you have to make sure whatever you see on LT Spice analytically also, you don't have to remember, you have the book. If you don't have one book, you can find other book. The equations are there. It's just your understanding that, okay, I'm getting by equations, I'm getting graphically, I'm getting by simulation or whatever, or I'm getting by hardware. 5-10% error is expected, okay, because the simulator is not perfect, the hardware components are not perfect, but it should match. So that's what. So now slowly we'll go towards equation, and good proof of this is theory of relativity, that Einstein gave the equation in 1 inch, and it can speak of the universe. Okay, so mathematics is God, I can say. Anyways, so a lot of things there. We are just zero in all those things. But if we understand, okay. So now the goal here, what I'm showing you here is that this figure almost you understood. Now see, this is very thin. Okay, and when the electrons are entering, or this all, let's say all 100 electrons are entering, this is thin, still thin, shown thicker here to make a point, but this is thin. So when there's so many electrons, they come here, right at this border, they will be the most, okay, and they will exhibit a gradient. and then they are collected all here, and once they come here, they are sucked. Once they are here at this point they are maximum, and they all come inside. Okay, and once they are here, they are all sucked and they come out immediately. So now we are going to study the concentration. From concentration, if you know the concentration, you can find out the current. So the current depends on, see, from this you can understand that the cross section of this, okay, it depends on how fast the electrons are diffusing. It depends on the doping of this. Okay, kitna doped hai. If this is comparatively lightly doped, you will have less number of electrons. So here we are going to study the concentration of the electron, and from that we will find out the current. Okay, so that's the goal. So now let us see. So here what is shown, as you can see, is this is the carrier concentration, and here we are talking of electrons, which is a minority carrier in the base. Okay, and this is the distance of the your PN NPN, and this is showing the emitter. This is showing the EBJ. Now remember, this is in the active mode. That is when your EBJ is forward biased, and this is reverse biased. So this is forward bias, this is thinner, this is thicker junction. Then the depletion region is established. Okay, and here is the hole concentration. Holes are moving from P type. Here it is shown in an enlarged way. Okay, just to make a point. So holes are moving like this way. So at this interface, the concentration will be highest, and then it will slow down as you go inside this side of the emitter. For the hole, it is atomic. And similarly, electrons are large in number. They will enter the hole, and the concentration will be maximum. Okay. So just think of this straight line now, because it is thin. Okay, it will follow the concentration, electron concentration, ideal this is. Okay, it will follow this straight line, and here it will be 0. Once it reaches here, it will be sucked. So this is just showing the concentration of the electron. Here it is hole, here this hole is the minority, here this is minority, and the concentration at this is 0. If you count distance, then it is NP0. Okay, so so it is given by this at this point of the interface. It is given by NP0, which is NPO. Or 0, you can see E raised to VB upon VT. Okay. Now, what are this? So, this is physics. Okay, and these are the equations that are well established. We have to accept it. We don't have to derive anything. So, this is at this interface at the starting of your base. Okay, so that is 0 here. So this is the concentration of the minority carrier. Here minority is the electron, okay, at a position X. So this is the distance, this is position X. Okay, so here for this NP0 here is for the electron, for it is here 0, we are counting, and then it will go ahead. So, and then it is a product of NPO 0, you can see it is to be B upon VT. Now VB, you know already, it is a voltage at the base emitter junction we have given, and that was forward biased, and this is the thermal voltage, right, VT, that was there in the diode also. And this NP0, this term is known as the thermal equilibrium value of the minority carrier concentration. So at thermal equilibrium, now this is operating at some voltage, okay, sorry, at some temperature, but this value is at the thermal equilibrium. Now this is physics, and these values are for a particular concentration and this cross section and all this is defined. This is quantified value. Okay, so this is the thermal equilibrium value of the minority carrier. Here it is electron. Ideally it is a straight line, but now as you know that since there is a recombination also, because there are holes and some will combine with that, it will follow a tapered kind of figure here. Okay, so it is little bit tapered, which you can see by this dotted line. Okay, so this So because of the recombination, it is bit tapered, or you can say curved. Ideally, it is, I mean, it's not a straight line, but in our calculation, it is almost as a straight line. We can take it because this is really thin. The base is really thin. Okay. But because of the recombination, it is tapered or curved. So just to make a point why this. And now, yeah. So this is the concentration we are talking of, the electrons, and then from that we are going to derive the equation also. So concentration of minority carrier NP at the boundary of EBJ is defined by 5.1 that we had just seen. Okay, and the concentration of minority carrier NP at the boundary of CBJ is 0. This of the minority, that is the electron at this boundary, CBJ is 0 because it comes here, they are sucked away. I'm talking of an active region. So we are already giving reverse bias, here's forward bias, and then this is the case. If you are not giving voltage, this is not the case. Okay. So, and yeah, so that is 0 as we have just seen. So positive VCB causes this electron to be swept across the junction. So that's why reverse biased. Okay. And this concentration NP 0 with distance, you can write it is a function of distance, but you can see this term here. Yeah, it relates to VBE and not VCB. VCB is not there as far as it is reverse biased. So tapered minority carrier concentration profile exists, as I said, right? But and this is the ideal one. It causes electrons injected into the base to diffuse through the base towards collector, and as such electron diffusion current IN exists. So now from whatever we this, right, what is this? It is a concentration of the minority carrier, and from that this concentration will result in a flow of electron, and that can be given by this equation IN. Okay, so electron diffusion current exists. Now, if you see this diagram back, right, this current is because of the diffusion, and electrons are more in number. It is because of the electron. So this is IN, and that is given by the concentration, right? So this NP0 is vital in that. So IN is given by AE, that is, what is this? This is the cross-section area of the base emitter junction where it was generated. And then Q is the electron charge. We have to multiply that many electrons. And then this is the diffusivity in the base. Okay, and this is the diffusivity in the base. And this, and then here, this is the concentration of the electrons, the minority carriers. And X, if you keep this is a distance from here, so this is 0, and X for the width of the base to be W. The maximum here X is W, so we are counting with that respect. And if this is the change in the concentration with respect to the distance, and for base of W, we can write this and simplify this as this, because this is dx is W here, the change from 0 to W, the thickness of the base, right? And this is simplified equation of this, and that is IN. So it depends on the diffusivity of the electrons in the base, the cross-section area, and the charge of the electron, and the concentration, as we have seen here. So some diffusing electrons will combine with holes. We have already seen base is thin, however, and recombination is minimum. And recombination does, however, cause gradient to take slightly curved shape. And the straight line is assumed, but we'll assume the straight line, but because of the recombination, there will be a little curve in this. Okay, so now it is observed that most diffusing electrons will reach the boundary of the collector base depletion region. So it is reaching this boundary, right? It has reached, and from that we created a current by giving a reverse bias. So this reached this boundary. It's telling the same thing what I have already explained to you. of the collector base depletion region, and because collector is more positive than base, these electrons are swept into the collector, and the collector current IC is approximately equal to IN. So we can say that this IN which was generated at the emitter, right, and it is making a current IC, so that IC is equal to IN, we can say that. And you all must agree to that without any objection. So IC is equal to IN, and we can write IC is equal to IS. So here, if IC is equal to IN, what I'm going to do is that this term IN, right? So this we will keep. So this term, you take this derivative here. Sorry. Okay, yeah, this is equal to this. Okay, that we had seen. So keeping this constant, we will keep, and then this term which is VBE raised to upon VT. Right, it is IC is equal to IN, that is IS e raised to VB upon VT, where IS is equal to this term. Okay, from all these before equations only. And this can further be simplified, this concentration, as Ni square upon Na, where Ni, again, this is physics, this is the intrinsic carrier density. Now, intrinsic means in the pure form, without when it was, if you want to find out the concentration doped one, this is for the in the pure form, and then the doping concentration of the base. So it is Ni square upon Na. So Is, if you further reduce this, it is equal to this, okay, and into E raised to VB upon VT. So these are all the terms. So if it is, so you can say that this IC is directly proportional to IS, and IS is proportional to the, if more the cross-section area, more the current, and if thinner the base, more the current. Thicker the base, less the current, because then everything will be lost in recombination only. If this is thick, you make it thicker, then less collector current will appear, right? Because things will be lost in recombination only. So thinner this is better, higher the cross section, more the current, thinner the base, more the current. So that all things should be logical in your mind, and by equations also you can see that. Okay, and Dn is the diffusivity of the electrons, and then magnitude of IC is independent of VCB. You see, it doesn't IC. It doesn't depend, as just talk. It doesn't depend on this as far as it is reverse biased. It only depends on VBE, which is here, as you can see here. IC is a function of VBE and not VCB. And as long as current is collector is positive with respect to base, or it is reverse biased, you can say. And the saturation current IS is inversely proportional to W and directly proportional to the area, cross-section area. And typically, what is the range? It is in 10 raised to very low. It is 10 raised to minus 12 to minus 18. So pico, less than picoampere of current, and it is also referred to as scale current. So this is the terminology that we use. So now next time I will start with this base current, and then the IC, all this current and how they are related. So some more parameters ahead which establishes the relation, then the model, right, and then how the graph is, how it looks. All these things we'll be doing slowly with some set of equations. Okay, so any queries you can tell me. I hope I was audible.
Ma'am, can you please share the slides?
No, yes, I'll do it once I get my lecture. Now, both the lectures and this slide. Of course. Anything else? It's all from your textbook. So you can read in if you don't still understand what I am talking, but I am always there. You can ask me. Anyways, I'll leave you. Have a nice day then if you have no queries.